Okay, how about now?
Does it sound good in the room? We got thumbs up. All right.
Okay, awesome.
All right. Cool.
So let me know when we can start.
Is the recording started, Sarah?
I just started.
All right, so you can go ahead and start.
All right, awesome. Well, hi everyone. I'm really sorry that I can't be there with you. I'm sorry to miss out on that great pizza, but yeah, I'm a little bit far away for that. Now, but the good news is that this way I could give you this talk. And why I wanted to give you this talk is because as .NET developers, perhaps you are not aware of a superpower of yours, which is that with your existing knowledge, you can actually create computer chips. This sounds like magic. It partially is, but we use a tool called Hastlayer for that. That will be the topic of my talk today. But before that, a little bit of introduction about me and where I'm coming from. I'm Zoltán Lehóczky. I'm one of the co-founders and managing directors of the company Lombik Technologies. We are mainly focusing on web development with the open source ASP.NET Core CMS Orchard Core. So if you are a web developer in .NET, I highly recommend you check out Orchard Core. It's a great CMS, otherwise a great web framework. And in the last 10, 11 years, we have worked with Orchard and Orchard Core and acquired clients from all over the world, actually, mostly from the US. We are a company based in Hungary, by the way, and so that's why this is more interesting. The municipal government of Santa Monica, for example, or Live Nation, or the Smithsonian Institution are all clients of ours, and Microsoft was at one point too. But when we are not doing web development, then we are doing research and development. For example, our Hastlayer project, which is fully open source, and every piece of code, every example I will show you today is also up on GitHub, for which I will also show you the link. But first, let's actually talk about you. Now, let's suppose that you are working on a project where you are doing some kind of heavy number crunching. And by number crunching, I mean something in the areas of, for example, AI, machine learning. Of course, pretty fashionable topics nowadays. Or you do something with images. Image or video processing are technically quite similar. Computer vision is something like this too. Or you do algorithmic trading on the stock market, perhaps even high frequency trading where every nanosecond counts. Or your application does some heavy data compression. Or your app needs to do a lot of cryptographic computations, or perhaps it does something with cryptocurrencies. Well, then you perhaps want to make your app faster. Specifically, you want to make some algorithmic parts of your application faster. And, well, what can you do? Then this is the usual runbook as a .NET developer. Because first, you, well, try to figure out what is slow. And, well, the step for that is profiling it and trying to optimize that issue. Let's suppose that that's something you have already done. Then you can parallelize your algorithm. So if it was single-threaded before, you can make it multi-threaded with tasks, with the task parallel library, or you can utilize operation-level parallelization, vectorization, single instruction, multiple data approaches. Let's suppose that you have already done that, and at this point, you basically use all the resources of a single computer, but of course, you can use multiple computers, multiple servers. You can scale horizontally, or you can use faster computers and scale vertically. let's suppose that you have either already done that as well, or it's unfeasible to continue. So at this point, just simply throwing money at the problem doesn't yield you enough results. Well, what else can you do if you are in this situation? You can look into heterogeneous computing approaches. Specifically, what I will talk about today is using GPUs, video cards, or FPGAs. Now, what's FPGA? Let's talk about that a little bit more. FPGAs, or field programmable gate arrays, are basically computer chips that can behave like any other computer chip, with the limitations, of course. Now, at this point, I would ask the room who has worked with FPGAs before. Unfortunately, I can't see you while I'm presenting, so so that won't really work. But perhaps not many people here have worked with FPGAs because, well, it's not something related to .NET, and it's not something related to software development either, because it's hardware development. Now, even if you haven't worked with FPGAs before, I'm pretty sure that you have used them. For example, if you Google something on Bing, as they say, then you have used FPGAs because Bing is accelerated by FPGAs. I'm talking about the search engine, not the large language model, which was at one point called New Bing, I believe, and now it's just Copilot. Or if you are using Azure, the networking in Azure is accelerated by FPGAs too. But FPGAs are sometimes also found in household appliances like routers, or less household appliances like X-ray machines, MRI machines, or even self-driving vehicles. Now, the thing is, as I mentioned, that to utilize an FPGA, you have to be a hardware engineer, or possess at least hardware engineering knowledge, since it's pretty much logic circuit design. You are creating a piece of hardware, even though you don't have to go to a foundry to get the chip manufactured, still is the same concept. Now, why would we use FPGAs, or why am I talking about FPGAs here? And the reason for that is that FPGAs have some unique computing benefits. There are certain things that they are very good at, and much better than CPUs or GPUs. So let's have a very crude, totally unscientific comparison of these devices, just to give you a basic idea. But of course, everything here highly depends on the specifics of your application and the specifics of the devices being used. So let's talk about parallelism first. So how many things you can compute at the same time? The first chart. Now, CPUs are pretty much on the lower end here, because with a CPU you can have 8, 16, 32, perhaps 64 cores, but that's about it. That's the hardware level parallelism you can get. With GPUs, it's on the other extreme, because GPUs are highly parallel devices with thousands of little processing cores. Now, these are very different very different from a CPU core. They are much, much simpler, but still the hardware level parallelism you get is in the order of thousands. Now, FPGAs are kind of in between. There are no cores on an FPGA, so to say, but the degree of parallelism you can get there is somewhere in between, in the order of hundreds. Now, secondly, let's talk about the complexity of programs you can run on these devices. So when it comes to a CPU, it's pretty much universal. If it's a piece of software, you can run it on a CPU. Whereas with GPUs, again, they are on the other extreme here, but on the lower end, because the programming model of GPUs is much more limited. It's not a general purpose computing device like a CPU. Although with GPUs, they are general purpose, but still the programming model is not just for any kind of computation, but just very specific ones. Not a big surprise. those are graphics computations or computations that are similar to graphics computations. And FPGAs are again kind of in between here, although you don't really run software on an FPGA, but rather you turn your software into a piece of logic hardware on an FPGA. And the complexity, depending again highly on your application or on the device, is somewhere in between, I would say. And lastly, let's see the power efficiency of these devices. So how many things you can compute with 1 watt of power. And CPUs and GPUs are roughly on the same level here, I would say, but FPGAs are really power efficient. The reason for this is that on an FPGA, you can get away without waste pretty much. An FPGA is not running other software. It's not running an operating system. It doesn't even have an instruction set like a CPU or a GPU. It's all bare metal. It only does what you need it to do. And because of this, it can be very, very power efficient. But the big issue here is that utilizing FPGAs is very hard. As I mentioned, you have to possess hardware engineering knowledge because programming a CPU, everybody can manage. Programming GPUs is not that harder nowadays, but using an FPGA is something completely different. You are not running a program on a device, but you create a piece of logic hardware. You have to think in terms of gates and wires and clock cycles. It's super, super low level. But with tools like Hastlayer, we intend to bring this complexity down all the way to the software development level. Speaking of which, Hastlayer is a tool that takes a computer program and turns it into a piece of FPGA logic. Or we could also say, and that's kind of the easy to digest tagline, or the nice sounding tagline, is that it takes a computer program and creates an equivalent computer chip out of it. Or we could also say that there's some logic in your software. We try to process your software and get that logic out of it with Hastlayer and create an equivalent logic in a hardware form. And we are at a .NET meetup, so of course we are not just talking about any software, but .NET. And it's actually .NET, not just C#, but every .NET language, at least in theory. So that means that apart from C#, also Visual Basic, or C++, or functional languages like F#, or even scripting languages can be used. We actually also have not just C#, but F# samples too. So all in all, what we want to get at is to get all the computing benefits of FPGAs for all of us software developers. This means that, well, first, you can get a very substantial performance increase if your algorithm is compute bound or memory bound and it's highly parallelized. Secondly, you can get a much higher power efficiency. And thirdly, this is still software development as usual, as we'll see in a minute, or rather in a second, because enough talk until now. Let me show you the whole thing as a demo. So now I'm switching over to Visual Studio. And what you see here is one of the Hastlayer examples. Again, all of this is open source. You can check this out and all the other samples on GitHub too. Now, this class here, this sample algorithm here is called parallel algorithm. And you might not have guessed, but this is an example of a highly parallel algorithm. This is not something useful, by the way. It's kind of an exaggeration of the kind of algorithms that are especially suited to be accelerated with Hastlayer and with FPGAs. And this is what it does. Let me scroll down a little bit. What it does, the core of the logic is pretty much here. it's some mock logic simulating some number crunching, because there's some conditional logic here, which is executed in a for loop 10 million times. And what's more important is that this is done in a task. Now, I guess everybody here is familiar with the task parallel library, but if not, you can think of these tasks as an abstraction over threads. Pretty much we are starting threads here, but the .NET task scheduler will make sure that we are not overloading our CPU. And how many tasks we actually start is here, which is 260. Now, why 260? I have an FPGA here that I will also show you. And when this is turned into a piece of logic hardware, into a piece of FPGA logic by Hastlayer, then these tasks will be turned into actual parallel processing cores. And 260 will fit on my FPGA here, which is a quite small, slow development board. So when we run this on our PC, on the CPU of a PC, then these tasks will run on the CPU cores. How many CPU cores you have, that many tasks you will be able to run actually in parallel. For certain CPUs, actually twice as much due to hyper-threading. But on the hardware, on the FPGA, the hardware level parallelism we will get will be in these 260. The rest of this class, or rather the rest of this method, is just some plumbing, because we wait for these tasks to finish, and then we sum together their outputs, which will be the output of our whole algorithm. So let's actually see it in action. And what I will use for this demo is this device here. I hope you can see on the other side well enough as well. I will also show you some close-up pictures of this. Now, this is, as mentioned, a relatively cheap, relatively slow development board. But what makes it special, and why I wanted to use this with you instead of using an FPGA in the cloud, like in Azure, which is also possible, because this is the same thing as the onboard computer of a satellite, which makes it a little bit more special. So this thing, and actually the smaller thing in the middle, goes on board of satellites too, when we are talking about new space satellites by space startups. And you as a .NET developer can actually write .NET software for the onboard computer of satellites in a hardware accelerated way. How cool is that? And since this is an external device, I will open a terminal and connect to it via SSH. Now, this device here runs a small Linux. I open the shell to it, and now I will run a demo script. What happens here is that, well, first Hastlayer generates the hardware, and then it starts to execute this parallel algorithm that I've shown you on the CPU of this device. Because this also has a CPU, well, that's why Linux is running. It's a small 2-core ARM CPU, very similar to the CPU that you have in your smartphone. But it's packaged together on the same chip. There is also an FPGA. So after the software execution, which just finished, it will also execute the same thing 3 times on the FPGA. And now this happened. So let's see some results. Here's the first one. The CPU execution took around 25 seconds, give or take. So this is actually pretty taxing for this ARM CPU here. For this we actually had to wait. Now let's see how long it took on the FPGA as hardware. If we scroll down a little bit, after some some debug output and some informational output. We'll also get to the answer on that. And here it is. It took around 240 milliseconds when we only take into account what happens on the FPGA. But if we also calculate in, or we also factor in the time it took to get the data from the .NET software to the FPGA, do the computation there, and get all the data back, then it took around 330 milliseconds. And actually, this is not the best we can do, because remember, we are in .NET, and .NET uses just-in-time compilation, there are caches, and otherwise the first run of a .NET application, or a method even, in .NET will always be slower. So if we check out the second run, which is here, then we'll see that the hardware part of the execution still took around 240 milliseconds, but altogether, it took around 245, so much, much closer. And this is about 100 times faster than the 25 seconds that the software parts took. So now, of course, this is, again, not a real-life example, but still, this shows you that with not much work, you can make your algorithm run 100 times faster with FPGA hardware acceleration using Hastlayer. Now, you may ask that, okay, we have seen this parallel algorithm, but where's the rest of the software? And you are very observant to ask that, because I haven't really shown you that. Now, this parallel algorithm class here is indeed just the algorithm. It's just the core of the computations that we do, but you also have to somehow use this from the rest of the app. And what I have here in this sample is a small console application, super simple, and this uses that parallel algorithm. And this is how you would do it. So this is how you integrate such an offloaded computation and Hastlayer accelerated external computation into the rest of your software. So you can imagine this is a cloud worker that you have here, or some machine learning application, or some computer vision application that's now offloads the slowest part of itself to Hastlayer. And how it works is that, well, first we create a Hastlayer shell, and then there's some configuration. The most important thing here is that we have to tell Hastlayer which classes have to be accessible from the outside, from the host PC, or from the CPU when we are talking about a device like the one I've shown you. And pretty much we tell Hastlayer here that, well, we want to run parallel algorithm from our host 2. And then comes the hardware generation. This is where most of the magic happens. This is where Hastlayer creates the hardware implementation, which is, by the way, a piece of hardware code. So just as we can write programs in a programming language like C#, you can also create logic hardware in the so-called hardware description languages. That's what Hastlayer generates. That's where the hardware implementation of your original software will come from. And here we tell Hastlayer to process the assembly of parallel algorithm. And finally comes the most important part, when we actually run the whole thing. So this here is where Hastlayer executes your algorithm. The execution itself is this run. So this is the same run method that we have seen in the parallel algorithm class. And as you can see, the special thing here is that there's nothing really special. This is just calling methods as usual. And why this works is that on this line, Hastlayer wraps your object, the instance of our parallel algorithm, into a so-called proxy, a dynamic proxy. Pretty much what this means is that when you call run here, then Hastlayer will be able to hijack those method calls and offload them to the hardware device, to the FPGA. And by the way, what this also allows you is that dynamically you can decide on whether to transfer a method call to the FPGA or not. Because of course there's always an overhead. This hardware acceleration only makes sense if your algorithm actually takes a substantial time, meaning at least multiple dozens of milliseconds. It's even better if it takes seconds or more. Now, if the execution time of your algorithm depends on the inputs, then you can dynamically decide whether it's worth to offload to the FPGA or not. Now, this is how you integrate Hastlayer into your application. And I've also shown you how the algorithm itself looks like. But let's actually talk a little bit about the hardware itself next. So let me go back to the PowerPoint, and let's see what this device I've shown you and used for this demo. This is the FPGA port, and that little chip in the middle, that's actually the FPGA chip, or rather that's the chip that has an FPGA and an ARM CPU in the same package. This is by the way called a Zinc. This is a device, this is a product by the FPGA manufacturer Xilinx, or rather AMD, because AMD acquired Xilinx. And this smaller board was actually plugged into this bigger one. That's the whole thing that I've shown you. This is a development motherboard. If you use it to have ports and be able to easily connect to the FPGA port. Now, one more thing related to hardware is something that I would like to show you is a piece of hardware code. So let me go back to Visual Studio and let me open the output folder of this application. Now, to be frank, this code file here wasn't generated right now because I'm now on my local PC, whereas of course what I've shown you was the demo I've shown you was running on an external device. Now, this is the code that Hastlayer generates. And remember that I mentioned that Hastlayer creates hardware code? Well, this is it. So what we are looking at now is something similar to a program. You can see that we also have packages here. There's an if-else. So this looks a lot like BASIC, perhaps. But don't be fooled, this is not a program. Some parts of it do look like or are similar to a programming language, but this is not a program. This is actually describing a piece of hardware. And if we scroll down a little bit, we also see a lot of differences. And specifically, this here is something interesting for us. Because what we see here are some type declarations for our parallel algorithm. Sorry. So what we see here is a little bit similar to what you'd have in C# for variable declarations or as properties. So these are just types and also some what's called here signals, but you can think of them as kind of variables. These are just type declarations and signal declarations for our parallel algorithm sample. The core of the logic is not here. For that, we need to scroll down a lot more. But why I'm showing you this is because this has an index which is actually 0. And if we scroll down a little bit, we see exactly the same thing, but now it has the index of 1 and then 2. So you now might guess where I'm going with this. If we scroll down a lot more here, this is generated code, and of course it's very, very long. If we scroll down a little bit more here, we'll see again exactly the same thing, but with the index 259. Now, remember, in Visual Studio, in parallel algorithm, we started 260 tasks here. And these 260 tasks were turned into 260 copies of what happens in those tasks on the FPGA. So these are the copies that you see here. And this is where the performance benefit comes from. This is why I said that with Hastlayer and with FPGAs, you will get that hardware level parallelism. So this here is pretty much a processor that can only compute parallel algorithm, but it can do that with 260 cores. And that's a lot. And again, this is just a simple device here. With large FPGAs, especially those that are available in the cloud, you can get a lot higher parallelization too. Now, what else is there? First of all, what we support with Hastlayer is something called Xilinx Vitis. Now, again, Xilinx is a transition name, I believe, because soon everything about Xilinx will be called AMD. But for now, let's call them Xilinx. And Vitis is their tool that you can think of a little bit as something like .NET, because you need to support, as an FPGA developer, you need to support Xilinx Vitis, and by doing that, you will gain support for a lot of FPGAs at the same time. It's not this easy actually, because you still have to work on supporting each device separately, but that's just the nature of low-level hardware development. But at least it makes things a little bit easier. And since we support Vitis, we support pretty much all the high-performance what they call data center accelerator cards, those FPGA devices that are available in the cloud, and not just Azure, by the way, but also AWS, Alibaba Cloud, and a few other smaller cloud providers have them too. And on-premises is also available, of course, just as I've shown. You can use the same cards locally in your own data center as well, and on board of satellites, as I mentioned, because FPGAs are also widely used in the aerospace industry. With Hastlayer, you can not just utilize that part, but also you can run standard .NET on the CPU part of these devices. We also did some benchmarks. So, of course, it's great to have this 100 times faster that I've shown you, but not everything is that good. And we got lower speeds and power advantages on the big data center accelerator cards. Those are, by the way, called Alveo and Xilinx Alveo. These are the cards that are available in Azure and in other cloud providers. We tested a couple of samples, and we got something like a 4 times, a 30 times faster performance with 20 to 120 times less power consumption. Now, power consumption, of course, can be interesting for you directly if you have your own data center, or at least somehow directly pay for power. And in that case, actually, you pay for power twice, because you have to pay for the electricity, and then you also have to pay to dissipate that heat, to cool it away. And when in the cloud, this transforms into cost savings for you. We also did some benchmarks with this Zing device that I've shown you. The numbers there are actually much better. And so we got something like between 20 to 120 times faster execution, with also between 20 and 150 times better power consumption. The details of these are, again, up on GitHub. So we have more numbers there. You can also read about the methodology, the specifics of the devices. So you can see how we came up with these numbers. One other curious thing is, which is actually quite interesting in machine learning applications, is custom number formats. Now, when you store numbers in .NET, I would guess that most of you don't really think about it too much, just as me, because, well, if it's a whole number, you store it as an integer, probably as an unsigned integer. If you want to store bigger numbers and you don't need negative numbers. And when you want to store fractions, then you just use double, perhaps just float. And when you want to store numbers for financial calculations, then decimal. But pretty much that's it. We, as .NET developers, we don't really need to think about number formats because that seems like a solved problem, but it actually isn't. Interestingly enough, with renaissance of neural networks, something like 5-10 years ago, the custom number formats became more interesting, because for neural networks, and this includes large language models as well, you don't need large numbers that are very accurate. You can use much smaller numbers with fewer bits, which are still good enough. And with that, you can save on memory and have a better performance. There's such a number format called POSIT, which is useful for such scenarios as well. This was invented and is developed by a mathematician called Dr. John Gustafsson, who works in Singapore on this. And POSITs promise to be better than the IEEE floats that we use. So that includes float and double in .NET. And at the same time, they promise to be better with fewer bits. Now, why I'm talking about this in the context of Hastlayer and FPGA acceleration is because with Hastlayer, you can also take such a number format and turn it into a piece of hardware as well. This is what we actually did, because we created a .NET library that includes, that implements POSIT as a .NET number format. We pretty much created POSIT structs. And then, since it was Hastlayer compatible code, we turned it into a hardware implementation with Hastlayer. So pretty much, even if you create your own custom number format, you can have your own processor for it. We have a few plans for the next steps. We want to have, first of all, more use cases. So if you do some kind of high performance computing, or if you have a .NET application that does some heavy number crunching and you want to optimize it, please let me know. I would be more than happy to help you get going. We also can engage into a partnership with the Wigner Research Center for Physics, which is a leading scientific institution in the EU. And they test Hastlayer with scientific computations. Because, of course, when it comes to physics, and especially particle physics, there's a lot of number crunching. Sometimes applications takes weeks or even months to run. And FPGAs are coming into every data center out there. So it's not like it's a specialty. It's not as common as having GPUs, but still more common than having any more special kind of hardware accelerators like for machine learning tasks. I didn't mention it yet because we don't really support those kind of FPGAs, but not just AMD is an FPGA manufacturer, but also Intel, because Intel also acquired the then second largest FPGA manufacturer called Altera. And well, AMD followed suit a couple of years later. So let me wrap up. If you like this, and I really hope you did, check out the SDK on GitHub. That's where you would start. All the samples, all the documentation, everything is there. Hastlayer has some further components, but these are also all available on our GitHub as well. And purely because I think FPGAs are coming. I see a similar shift with FPGAs than it was with GPUs. Because, you know, in the very beginning, GPUs were just for games, just for graphics processing. And the people who worked with them worked with graphics processing. But then people started to hack around, and eventually GPU manufacturers created GPUs that were not for graphics computations, but for general purpose compute acceleration. And a similar shift is happening with FPGAs. Those data center accelerator cards I mentioned, that's why they are available in Azure, because Xilinx/AMD knows that this is a useful use case. So thank you very much. If you would like to get in touch with me, again, I would be more than happy to help you get going. Otherwise, check out the Hastlayer website and the SDK on GitHub. Or if you are interested in the company behind Hastlayer, check out our company website under lombik.com. Thank you.
Thank you.
Thank you.
All right, do we have any questions here at all? In the room, you've got the, we can do now, or I can turn the recording off, and then we can ask the questions. Maybe we'll do that, just in case people are shy. It's over there, so I can't hit it. Of course, I can always edit it out after, you know.
So it seems everything was clear, or nothing was clear.
Everything was clear.
All right, that would be great.